I think there are a few more over there, right? Ashwarya. It's okay, no problem. Okay, while we are waiting for them, I think there are some questions just now about modeling of soil. Usually for sand, I think there was the first question was on sand. Was it correct? Someone asked me about sand. Who asked me? I think was it yourself? Okay, basically, yeah, I think you're right. The sand behavior is a bit funny because sand can quite commonly can give you this kind of thing. Right? Usually, what I would suggest to people is this: if you are sure you get onto here, okay, then what you do is you can just go across like that. But then this part here is unconservative. This part here is unconservative. If you want to stop here, then it's a bit awkward. It's a bit awkward, you know. If you want to capture it approximately, then what I would do is to go like that, so that this part here is about here, and then I'll go this way to turn it around that way. That way it's more conservative. You see, so there's another way, basically to use a reduced friction angle, and then let a dilatancy takes its course. That's the thing. Okay, so this is, but there are lots of sand models. The only thing is that you don't have the parameters. So getting models for sand is also a issue, you know. So that's one thing. The second thing you asked, I think, was bouldery clay. Okay, bouldery clay essentially are clays that has got boulders inside. I do not know what is the origin of the bouldery clay in India, but in Singapore, the speculation is that bouldery clay is because some cliff or some slope in the historic past collapsed, and then you got big boulders embedded in the clay matrix. And so, okay, usually what we do is this: we ignore the boulder if the boulders are not in contact. Malcolm Bolton in his books basically did a nice analysis in which he said, if you have particles, coarse particles and fine particles, and the coarse particles are, if the fine particles exceed about 35 to 40%, then you can quite easily show the coarse particles are generally out of contact with each other. They are just individual particles floating in a matrix of fines. And what he says is that in this case, then the behavior is more clay-like. It's governed by the fine particles, which is the clay-like, because you can only get a coarse particle behavior coming in if there's friction between them. If there's no contact, there's no friction, then the fine particle will govern. So basically, from the point of view of strength, very often when we model bouldery clay, we ignore the boulder, because in a sense that is also conservative, because the effect of the boulder is, if anything, to strengthen your soil, because if there's a slip plane going through, it will have to avoid the boulder. So it will, if anything, strengthen it. So if you ignore the boulder, you are in a sense being conservative in a certain way. The only problem with boulder is that the thing that we need to watch out for is that when you're driving piles, or you're doing boreholes, or you're doing cone penetration tests or something like that, driving piles is a real issue, because you hit the pile, hit the boulder, you do not know whether you hit the bedrock or whether it is a boulder. Okay, and I have personally been involved in a project where the pile hit. Well, there was a whole corner of the building where there were a lot of boulders, and many of the piles hit the boulder, and the piling contractor, okay, basically thought that he had hit bedrock, so he terminated the driving. There was no additional piles being installed to transfer the load across. So he terminated driving, and then over a period of about a year, the building was settling. Okay, it's quite a scary situation, because the lift shaft would be moving 1 millimeter, quite steady rate, 1 millimeter every 3 days. So, and there's no stopping it. So basically, as an engineer, every 3 days, you kind of know that you're 1 millimeter further out. And 1 millimeter. So basically, by the time they discovered it, the guy has already moved out 200 millimeters. 200 millimeters. All right. And it's a funny situation. You know, in these tall buildings, 30-story buildings, they have curtain walls, which are big glass walls. They come in with a curtain wall, they couldn't put the thing in because the frames are all distorted. Then they went up to the top of the lift shaft, they did a plumb line, And they found that the top of the lift shaft was off vertical by 200 mm. And that was when they suddenly realized that was a big problem. The whole thing has been tilting for the last don't know how many months. So they came to find us. So there was a big remedial job. It was quite a major thing. So, but in terms of modeling, I mean, the Fort Canning tunnel went through the Fort Canning boulder bed. We actually model it as a residual soil. But I don't know whether the bouldery clay you encounter here, is it residual material or is it in other material? Correct, but the clay itself, is it a residual material, weathered soil, or is it soft soil or what? Residual soil, right? So it's what we call weathered residual soil, and it's quite common. It's quite common. So I would, in fact, I had exactly the second case study was on this. Fort Canning, I just model it as a more Coulomb because, okay, the first, one thing about you need to do in finite element study is to do a parametric study. If the problem shows itself to be very sensitive to the stiffness, then you know that it is actually a fairly safe problem because you know that it's controlled by modulus. If it is not sensitive to stiffness but sensitive to strength, then you know that you have a very low factor of safety. It's almost like you're on the tail end, so you got to be careful with that thing. So with that problem, that was the first thing I did, was to do a sensitivity study. Immediately I found that, wow, it's completely almost proportional to the stiffness. Then I know that this is a problem that is governed by the stiffness. So basically, I just model it as a more Coulomb with the angle of dilation. I think I was using abacus. I was using like 0.1 degree or some very low angle of dilation. And then I use what I believe to be a reasonable modulus for that E50 for that soil. So I went for it and it worked out okay. Actually, the answer was, maybe I was lucky, but the answer was remarkably good. I mean, we were like within 5%, 10% of the answer. So which in FEM is actually pretty good. So this is bouldery clay. It's in the Fort Canning boulder bed. So this is one of those things. What are the other questions you asked? Oh, applicability of chem. Usually people don't apply chem clay to sandy soil. You remember when you say sand, people will say, let's go more Coulomb. And in a sense, there is a how should I say, there is a reason for it, because very sandy soil has a cap. Okay, but the cap is very far out. If you do isotropic compression or one-dimensional compression on sand, you don't usually get to virgin compression until you're past 1 megapascal. And so basically, for most engineering purposes, people will say, that's not really that important. It means we are not going to hit that kind of stress level, so we don't bother with chem clay. Okay. I'm sorry I didn't realize that you are so because I purposely missed out. I missed out the part because there was not enough time, so I thought I have to do a bit of juggling. But anyway, okay, I'll give you a formula. I think I'll just give you a formula. There are several methods of doing it. The simplest method, okay, may or may not be the most accurate. None of these methods may or may not be the most accurate, but the simplest method is based on the index properties, which is Atterberg's limit. So I hope they are of some help. Let me see whether I can dig it out somewhere. This brings you to a real complicated formula. If you want, I can give you these few slides and you can take a look at it. That's the first method, which uses a certain formula. Let me just put a thing up on it. Okay, basically you got to crunch out this formula, and this point is itself, you have to project the one-dimensional consolidation curve backwards to 1 kPa to get to E1D0. So basically, there's quite a bit of thing to calculate. Now the simplest one, okay, is to use using moisture content and over consolidation ratio at the in-situ state is also doable, and this is the way Abacus use it to do it. So Abacus doesn't ask you for the ECS. Abacus just say, give me your moisture content and the OCR at the in-situ state, and they basically can calculate everything for you. And so I also have this thing you can calculate from there. All right. And then the third one, which I think is the easiest, is to use the liquid limit. Okay, the liquid limit. Okay, giving the liquid limit multiplied by the G plus lambda log of 2 over this thing. Okay, and this thing is Cu over P dash. Now Cu over P dash, we usually just guesstimate it to be about 0.23. That is not a bad number, 0.23, 0.25, 0.22. So basically you can I first, when I come up with this, my first impression was that it is so simple it cannot be any good. But after I compare a few methods, actually this one tends to be more robust. Maybe simply because it is the simplest. So if you like, I can see whether I can get this thing into a PowerPoint and into a PDF file and send it to you. And send it to, can I send it to you tonight? Yeah, I send it to Prof. tonight. Then you can, if I forget, which is not unlikely, please let me know tomorrow. Yeah, send me a message. You know my email, right? You know my email? Okay, send me a message. Yeah. Okay. Is it okay? Okay. Any other questions before we move on? Actually, I'm not very familiar with some of these parameters because there are so many parameters in the Plexis ordering. Let me just get pull out that slide so that we can see where we are. Oh, I know what is this. No. This is actually stiffness power dependency for stress level. Power for stress level dependency of the stiffness, because, okay, this M parameter, the stiffness or the modulus, the stiffness of a modulus. Oh, let me give you this, bring you back to this few slides earlier. That is easier to explain. You see, this one is from Ganesh Dasari in his PhD thesis. In fact, a lot of people noticed. In fact, back in 1950s alone, people already noticed that the shear modulus, is dependent upon basically the shear modulus degrade with shear strain, but it is actually a function of the mean effective stress as well, what we call the effective confining stress. The higher the effective confining stress, the higher the shear modulus. Now, basically, this is usually taken to be a power dependency. And so the M value is actually this N2, power dependency. You understand? So it's in what what is it a power of in terms of? So basically for clay and for sand, it is usually considered to be quite close to 0.5. 0.5, right? And for clay, the general thing, but this is just a general rule, that it is closer to somewhere between 0.5 and 1.0. So it's quite close to 1.0. So this is the kind of thing that people come up with. But if you want to be accurate, you really have to do your own test. Okay. Is that alright? So that is just a power dependency factor. Okay, anything else? Anyone has any burning question? Everyone fine? Okay, maybe we just carry on a few more slides because I want to finish off the last part so that I don't come back to it tomorrow and just go into the case history. Okay, we were talking about this thing before the break. So the question is, okay, is it okay? How do we model something like that? This is the black line. Those jagged black lines are actual stress path from actual stress path tests on Singapore marine clay. Okay, so the question is, how do you model something like that? Now, the first thing is this. That if this is actually PC here is P0 prime, P0 prime. Okay, there's a conflict in the in the terms used, but actually this should be P0 prime. Okay, because I was writing a paper for another conference and then I just put in PC prime, but this should be P naught prime. Okay, by our agreed convention, this should be P naught prime. So in a sense, this is the actual P naught prime of the soil. Now Singapore marine clay is a very funny kind. It's a structured material. Okay, and it depends a lot whether the clay is structured, is sensitive or not. If the clay is not very sensitive, then a chem clay or some soft soil model will do nicely. Wonderful, it will do nicely. On the other hand, if the clay is sensitive, nothing will do completely nicely. Nothing will do completely nicely. So you have to think about where you want to juggle. Okay? So basically, that is presuming that you sample the soil very well. Then you are able to detect this thing. And you are able to detect that in fact the soil looks as if it is over-consolidated, lightly over-consolidated soil. But if you don't sample the soil very well, if the soil is completely disturbed during the sampling, in fact it looks like an under-consolidated soil, because in the process of sampling, you shear the soil, you load the soil. The soil has gone through one triaxial compression and unloading. So you already generated excess pore pressure inside. The guy is completely remolded. He has got excess pore pressure. So you check out the excess pore water pressure and it looks to you as if the soil is still consolidating. You see, in the early days in Singapore, a lot of these incidents happened and people were all, the ground has never been landfill. There's no landfill over the ground. They went in there, they dig, the soil is under consolidation. Over the OCR, the over consolidation is 0.6. 0.6, which means the soil is under consolidated. So something must be wrong, you see. So basically this is the reason. And the soil is destructured when you drive your sampling tube through the soil. So if assuming that you do it properly and it's very careful, then you will see a situation whereby this guy is about 1.5. The over consolidation ratio for the marine clay would be about 1.5, and you will be able to capture this curve. So now if you see this curve, if you see something like that, okay, how do we model it? There's nothing you can do perfectly satisfactory. Okay, the first way to do it, supposing you say, I treat this as a chem clay with an over consolidation ratio of about 1.5. So my chem clay U locus would look like that. Okay, this is 25.4. This is the friction angle for the soil. And then I go up here, the stress path go up here, and then it stops here. But this is unconservative, which is to say, if you use the undisturbed over consolidation ratio of the soil, you end up being unconservative because your end point is here, whereas the end point of the soil is somewhere down here, which is much lower. So what is the problem? The problem is that the chem clay model is not capturing this part here. The chem clay model is unable to capture this downturn. It cannot capture that particular downturn. In fact, there are very few standard soil model in standard software that will capture. I don't think there's any, in fact, that can capture this downturn. So basically, if you cannot capture this downturn, you hang up here, basically, but the actual strength will come down to here. That is the big problem. That is the big problem. Okay? So the red area, I won't recommend. The red line, I don't recommend. Okay? The green line is to take the opposite extreme. I treat this as a normally consolidated clay. Alright? If you say, I don't sample the soil very well, it's come out completely disturbed, it looks like under consolidated, but I assume that it is normally consolidated. In fact, if you don't sample it well, you won't even see this PC prime, P naught prime. You won't see this. You only see this guy, something looking like that. So if you model it this way, then actually, ironically, you get it. The final strength is correct. Of course, the stress path is completely wrong. You generate a lot more excess pore pressure at the lower stress level. Alright, it's wrong. But the final strength is correct. The final strength is correct. Okay? Now, supposing instead of using the red line, if you have sampled the soil properly, you know that the P0 prime is here. The P0 prime is here. And you say, I want to tune it so that I can get this point. Well, one way to do it is you tune it so that your stress path comes to here. Now, how do you do that? One way to do that is to specify a lower angle of friction, which is a reduced angle of friction. So you can also use a reduced angle of friction for chem clay. You can use a reduced, and in fact, it was reported by Tom Henderson and Andy Pickle in the 2005, let me see, where is it? Pickles and Henderson's 1905 Underground Singapore paper, which says the friction angle which needs to be adopted in a modified chem clay type model must be artificially reduced to about 16 degrees in order for this model to generate correct undrained shear strength profile for analysis with deep deposit of Singapore marine clay. This bears no relation to either the friction angle of at peak strength or the critical state angle friction for the marine clay. Okay, so basically they are exactly saying that you have to artificially, because there is a destructuration process going on. Okay, there's a destructuration process going on. So there are several ways you can think about it. Okay, so this is the third method. Use PC prime as the initial pre-consolidation pressure, but with the artificially reduced angle of friction to accurately capture the critical state strength. Okay. The green arrow and the red arrow I already mentioned to you. The green arrow is to say use the original friction angle but ignore the over consolidation ratio. Ignore the over consolidation ratio. Okay. The red line is to say, the red arrow says use everything. Use the over consolidation ratio, use the original angle of friction, but it is unconservative. Okay, so it's not a recommended course of action. Okay, I think so. So this is what it is. I think that's basically it. All right. So this kind of things basically shows you that in fact, in natural soil condition, you may quite often encounter situation where neither the mock Coulomb can work, neither the chem clay can work, neither the soft soil work, neither the hardening soil work. Then what works? Nothing will work perfectly. You have to trade in which is the most important thing you must capture. And then those not important can't be helped. Is that alright? It's a question of compromising. Where you want to compromise your thing. Sorry? Yeah. Yeah, it's only for, that's why I said that this is making these two authors, their observation is for Singapore marine clay. Because they were talking in the underground Singapore, there was a big concern over the strength, modeling the strength profile correctly in Singapore marine clay. And this, you see, 2005 is just 1 year after the Nickel Highway. So it's still very fresh in people's mind. So people are still wondering, how should I do this kind of thing? It was in the same conference that Wong Kai-sin showed that the soft soil model will always over-predict the chem clay. And then, these two shows that the chem clay will over-predict the marine clay. Okay, so basically you can see why, actually it's quite complicated, the whole thing. But essentially the 70 degree is something you apply. But in order to come to that, the question is not whether it's 17 degree or 16 degree. The question is that you must have very high quality test data to show you what is the stress path of the truly undisturbed soil. And if you have that, then you can start to make proper decision. If you don't have that, probably the best course of action is to just forget about the over consolidation ratio of 1.6 or 1.5 and just simply treat it as a normally consolidated material. And probably the error, the notion of compensating error, that means you already make an error on the over consolidation ratio. Your error on the over consolidation ratio is conservative, but your angle is unconservative. So the two hopefully will balance each other out. You see? Because your angle is, basically it comes back to this. You see, your black line actually comes down to this. Alright? Basically, if you look at this green ellipse. The green ellipse is really the chem clay model using this as a normally consolidated soil. So this is the P0 prime. The considered P0, the assumed P0 prime at the start. So if you assume the P0 prime to be here, you assume the soil to be normally consolidated. And you ignore the over-consolidation ratio. So you say, I ignore the over-consolidation ratio. In that sense, I'm conservative. I'm conservative. But of course, the angle, if you had used the correct over-consolidation ratio with this angle, you would have been unconservative. So you are using that over-consolidation ratio to compensate for part of that error. Is that alright? Okay. So my sense is, it depends on what you have at hand. Because if you don't have good soil data, in all likelihood, if your soil data is disturbed, you probably wouldn't even aware of this. You wouldn't even be aware of this thing, this point existing here. You will probably only see this guy. And then you would, so actually it's good, okay for you. Except that down here you seem to generate a lot more. Your sample will appear a lot softer, more flexible. More flexible than the real sample. Is that alright? It will be more, the stiffness will be lower, but the strength is maintained. Okay. Oh yeah, some of them are CK0U, some are CIU, some are extension tests. You can see these are extension tests coming up. Okay. The CIU are the black lines coming out from here. I think there are some, I don't know why there are some lines that go like this. I'm just wondering why. Let me just take a close look at this. I know for sure that the solid black lines are the the solid black lines are the CIU. The solid black lines are the CIU, and the thick black lines are the CK0U. And the CIU you can see come out here and then come out this way. It come out here and then come out this way. So basically they are all hidden amongst the CK0U line. But the idea of this whole plot plotted together is that no matter whether you do K0 test or CIU test, the angle of friction is the same. But more importantly, we actually wanted in this chart. This chart was produced in one of the natural soil conference organized in Singapore, and we actually used this chart to show one point, that Singapore marine clay has a very special attribute, and that is that the angle of the M value for friction for compression is very similar to the M value for extension. Very similar. In most soil, the compression M value is larger than the extension M value. But in Singapore marine clay, they turn out to be, I don't know what was the word used. It's a surprising degree of isotropy. That was the word that we used, because I think it was David Hyde who gave it that word. I can't remember what it was, but it was something like a surprising lack of anisotropy. Okay, that was the purpose of that plot, to show that the two M values are fairly close to each other. Okay. Yeah, very good. It takes a lot of work, you know. It took a huge amount of work. I tell you, we had a lot of heartache, man. You don't look at a figure like that, you don't know how much work went into it. It's tremendous amount of work, you know. Chong Po Ting. I don't know whether you know him. Yeah, you know him. Okay. Now, any question before we move on? Any question? Okay, if not, then maybe I'll move on a little bit. Okay, and basically I just want to wrap up the modeling part, the soil modeling part, material modeling part, by saying that there are many ways to model this material, to model material approximately, but there's no such thing, no model in commercial software which will model it perfectly. Okay, and of course there are questions like, some people will ask, how undisturbed is the soil on the site? Nobody will know. Alright? But I would imagine that the soil on the site is so big, the mass, that even if you put a huge crane on top, it will probably not be disturbed very much. Right? I mean, of course, when you drive your sampling tube through, around the sampling tube, there could be a lot of disturbance. But I mean, this is where you need to use an engineering judgment to do it. And good modelers, I'm not saying that many times already, we need good modelers. Okay? People who know how soil behave in reality and how one can approximate its behavior without being unsafe, rather than good soil models. Perfect soil model will not be available for a long time. You can be rest assured. Until the day you retire, they will still not be available. Okay. So essentially, this is the thing. Now, the last part of the workshop, I want to say something about practical finite element analysis. Practical. I guess it applies both to practice and research, but research, finite element analysis are different. I don't know how you say. I don't know how. In a lot of research circumstances, the finite element analysis, from a geometric standpoint, may actually be simpler than a practical finite element analysis. Because a practical finite element analysis, if you say you want to model an excavation for a nuclear power station with all kinds of opening here and there, that geometrically can be quite involved. Right? Now, in a PhD study, usually we don't get a student to model all kinds of fanciful geometry, but something simple like a circular hole in the ground kind of thing. That is the kind of thing that we do. So research may be different, but there are also some similarities in the sense that in some cases, when you are going towards the tail end of your research, you may want to model something very realistic just to demonstrate. So the question is, what are the things we need to watch for? I mean, there are a lot of factors actually affect the accuracy of finite element analysis, and it's not just the constitutive model. So we should not get hung up on this constitutive model and say, if my constitutive model is no good, then everything else is messed up. No, it's not. It's not like that. It's not like that. Okay, it doesn't mean that you don't have to pay attention to other things. In fact, you should pay attention to other things. So the first thing about finite element analysis is that some things are always not obvious. You see, the thing is that I don't know whether it happens in India, but in places like Singapore and Hong Kong, there is a tendency in the engineering, I won't say in the engineering profession, but in the government service, the regulator, to come down with lots and lots. It's like a checklist, a laundry list of checklists that you have to go through, tick, 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 tick. I've done this, I've modeled this. I mean, to me, dilation angle equals to 0, tick. This equals to tick. I use method B, tick, 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 tick. That kind of thing, So basically, there's a tendency to go through that kind of laundry list. And the idea is that if you go through a laundry list, then it will be very safe. Actually, not necessarily so. Not necessarily so. I don't know whether do you do this or you are more flexible, you kind of like leave it more to the engineer's judgment. Down there, the engineer is almost like a guy taking off the laundry list. So in a sense, it's not very healthy. Not very healthy. So what I want to do when I produce this slide in one of the local conference, my point to people is that don't run away with a whole laundry list full of things that you think is the biblical truth. In fact, it's not. Which in fact is not. It gives you a false sense of security and say, now I've gone through the whole laundry list, my whole thing has got to be safe. It doesn't work. It doesn't quite work like that. So the first thing is it's difficult to lay down simple rule of thumbs. Very difficult to lay down simple rule of thumbs. And a lot depends on the problem and the variables in question. And that's why the engineer have to use an engineering mind's perspective to look at the problem and say, how is this thing going to likely to behave in any case before they even come out to the final answer. Okay? And one set of parameters may be conservative to some variables, but not to others. And so you cannot set any hard and fast rule in any complex problem because it will only lead to false confidence and then increased risk of errors. And then there is that people doesn't even know that they make an error. And basically, there are some simple things I always tell engineers to do in finite element analysis. Okay? The first is a consideration of the physics of the problem, to be able to understand the problem in your mind's eye. As the result unfolds, you keep thinking, is this a reasonable set of results? Is this not reasonable set of results? That's the first thing. The second one, very important, conducting sensitivity or parametric study. Very, very important. You know, there are still a lot of engineers in Singapore going around. One consultancy job, one run. I say, how can you get away with one run? Are you sure your parameters are so accurate, your run is going to be absolutely perfect? I said that, should you not allow the possibility that there may be some errors in some of your parameters, if not all of the parameters, and you would like to investigate what is the sensitivity of your answer to these parameters. And I thought that is actually very important, because there's no such thing. In a simple problem, you can easily say, I use safe parameter or unsafe parameter. But what I found is that in my experience, that if you try to do that in complex problem, without thinking through the problem, you actually get caught out. You can be caught out. Okay? So these are some of the things that I would urge people to be careful about. I want to just give you an instance. You know, just now, earlier on in the Moore Coulomb, I talked to you about the angle of dilation and how the angle of dilation has to be, is why people usually use 0 degree as the angle of dilation. Because in an undrained problem, it is the one that supposedly lead you to a lower strength. Okay? So basically, there's still a very pervasive notion in Singapore that we must use 0 angle of dilation. And so I did this job for one of the project, which is a common services tunnel. A common services tunnel in Marina South area in Singapore, where this is quite common now. It's a trench problem. You can see the struts and the chicken feet. These are what we call the chicken leg or whatever you call it. Okay? And then inside the excavation, even before they do the excavation, they pre-install the pile inside. I don't know whether this is common in India. Have you done this? This is quite common in Singapore. Before they do excavation, they already put the pile inside. Then once they finish the excavation, they don't have to go down there and pile the thing. They just go and cast the box on top, the base slab on top of the pile. So that's easy for them. So the piles are all there. So this, one of the big questions was, what is the effect of the excavation on these piles? On these piles. Okay? On these piles. Now, most of it is actually marine clay. In fact, I think this is marine clay. The grey area is marine clay over here. This is sandfield. This is sandfield. But this is actually a fluvial clay. This is a fluvial clay. Fluvial sand. Fluvial sand. So it's actually sand. See this area, this layer here is sand. So basically, you got a pile sitting through marine clay, and then with a reasonably thick layer of sand underneath. Okay? So I was using the chem clay model for marine clay. I was using the Moore Coulomb for the sand layer underneath. And this is loose sand. Because this is reclaimed land, and you can see a huge layer of loose sand over here. This is also sand. So I use Moore Coulomb here, chem clay here, etc., etc. So basically, it went through. So okay. And then I started to do my parametric analysis. And I found to my surprise that when you set a 0 dilation angle, the bending moment in the pile, here are smaller than if you set a 5 degree or 4 degree dilation angle. You get what I mean? That means if you set a 4 degree dilation angle, the bending moment is actually larger than if you set the dilation angle to 0. And the reason, so we start thinking about why there is this phenomenon happening. We thought there was some error in the analysis, but the analysis, we checked through the analysis, was okay. But so we started thinking about why this is the case. And it turned out that the reason is because this. When we use a 0 angle of dilation for this layer of sand here, alright, a 0 angle of dilation prescribes a weaker material, right? And a material that will flow more easily. So imagine this is a pile. There's a sand. 0 angle of dilation, the wall is here. The sand can easily flow across the pile. So the sand just literally moves through the pile. Okay, the wall will show a larger deflection. Okay, but the pile almost feel less load. On the other hand, if you set a 5 degree angle of dilation, then what happens is when the sand tries to shear across the pile, they lock up around the pile and they try to bring the pile along. And so the result, the pile was bent. And so it just tells you that the people will say, oh, you use zero angle of dilation, everything. I told the client, I said that if the authority want you to use zero angle of dilation, it is actually to your favor because your bending moment went down 20%. You know, so basically, after this, I told the Land Transport Authority, I said, look, don't always run away because the Building and Construction Authority always run away with this idea that zero angle of dilation is the most conservative. I said this is very simple. You know what this is? This is a situation where you got a load sharing phenomenon. A load sharing phenomenon. What is the load sharing phenomenon? You got a pile here which has some kind of retaining effect, right? Some kind of retaining. And of course the wall has a retaining effect. So the wall and the pile are sharing the load of the soil behind the wall. Come on, pushing out. Now if the soil here has a high dilation angle, then more of the load is thrown onto the piles here. The wall will move less. Your retaining wall will move less. Alright? But the pile will be subjected to more bending moment. If your dilation angle is 0, then the wall will move more, but your pile will suffer less load because more load is thrown onto the wall. So it's a load sharing problem. It's not a simple factor of safety, high, low, conservative, unconservative problem. So the material, the property can actually redistribute your load in a very subtle way that you are not, that you may, if you look at it on the surface, you may not be aware of it, but actually it is happening. So you have to ask yourself, okay, what should I do? So that's why when people ask me, what are the most conservative parameters to be used in all cases? I said, I learned from this problem, there's no such thing as conservative. You should do the parametric study and tell the client, if you're looking at the bending moment of pile, use 5-degree angle of dilation, this is the largest bending moment you've got to get. If you're looking at the movement of the wall, use 0 angle of dilation, that is the largest movement you get. Correct or not? That is what you ought to do. There's no such thing as a kind of a biblical truth somewhere that you list out all the do's and don'ts, you know. It doesn't happen. So at the end of the day, you still got to do your parametric study. Okay? So this is a simple example in which I kind of use people to demonstrate why zero angle of dilation is generally conservative, but not always conservative. Not always conservative. Okay? Because it's a load sharing problem. You're dealing with a load. Actually, modern systems are foundation systems are very complicated. It's not like a simple thing, this guy go on here and then they fail. It's like, not quite like that. It's not quite like that. Okay? Okay. I don't know whether you want to break off now or let me see. I got a few more slides to do before I go on to the. Okay, I just have a few more. Can I finish it first? Okay, modeling. Maybe I'll just clear through all the last few slides first. Then tomorrow we just. What do you all want to do? Sorry? Continue, Okay. I'll just finish off the thing, then we can go off. Okay. Now, when you okay, what about the structural behavior? The behavior of the diaphragm wall and the behavior of the. Usually we look into the diaphragm wall, the tunnel lining and the struts, all that. Usually I advocate using a simple linear elastic because you know why? An elastic system like a structure would attract the most load. So you tend to. You see, the thing is that in any case, you don't want to model a structure. If you want to model a structure as an elastoplastic material, then you have to watch for the plastic hinges and where it yielded. Because if you ever tell the client the diaphragm wall has yielded, I can tell you, he will tell you stop work straight away. Almost immediately you will stop work. There's no second. You know it happened. Yeah, that was what happened in Nickel Highway. Actually, the diaphragm wall yielded. All right, and you know why I know the diaphragm wall yielded? I had the complete stack of site meeting and recalculation analysis. All right, the system in Singapore for controlling excavation is quite complex. you have a alarm level at which you have to stop work kind of thing. And so the alarm level for that particular stretch which collapsed was set at 150. And you're supposed to go all the way down to 35 meters without hitting the alarm level. In the event, they hit the alarm level by the 4th level. There were 10 levels of excavation, 10 levels of struts. They hit it at the 4th level of struts. So you can imagine at the 4th level, the guy already gone. So they then did a reanalysis. And then on the day before the collapse, it hit 400 millimeters. Okay? They lifted the alarm level from 150 to 400. The day before the collapse, 19th of April, it went up to 400. Okay? And they immediately redo the analysis. And you know how they redo the analysis? I can tell you this is really telling lies with FEM. They reduced the stiffness of the diaphragm wall until it's about 30% of the original stiffness. No question asked. They say the diaphragm wall is okay, no problem. Since it's okay, it must be okay. I reduce it to 30%. Why? They have to match the deflection. They have to match that deflection, so they have to reduce the stiffness. Now, if you reduce the stiffness of a diaphragm wall down to 30% of the original stiffness, there's only one thing in my mind. The wall must have yielded somewhere. It has got to be. So it has definitely a plastic hinge somewhere, right near the bottom. So anyway, that is the situation. So usually I normally advise people to use a linear elastic analysis because you know why? The people who check the thing will be the structural engineer. So the moment you throw the load onto the structural engineer, he will know how to size the thing based on that bending moment and all that. So he will be able to size it accordingly. And you want him to use the largest bending moment to size. Okay? So this is the thing. Exception to this is when you are recreating a collapse. You are doing what we call geotechnical forensics. That means there is a collapse and you want to find out what's going on. Okay. Then you can use a non-linear analysis. And the nickel highway analysis, I'll show you some of the non-linear analysis that we used. Now, this is another. The second assumption is for components which are conventionally not subjected to structural design. And there are components because of the fact that when people design, they design in 2 dimensions. You see, if you have a deep excavation or wall, it's always done in 2 dimensions, top to bottom kind of thing. But between one diaphragm wall panel and another diaphragm wall panel, in fact, there's no steel. No steel. There's a key, concrete key, just for water tightness. Water tightness, there's a key. But there's no steel. So there's always a question as to, is there continuity at this particular point? Where one wall key into another, what is the effect of this key? Okay? So this is the issue that as a geotechnical engineer, if you are doing full 3-dimensional analysis, you got no choice but to think through some of this. Similarly with the linings in tunnels, when you look at the linings in tunnels, the segmental linings, very often the linings the linings are designed so that the steel reinforcement is circumferential. And there may be a few rebars, starter bars going out, but not too many. So when I ask tunneling engineers, I say, what is the longitudinal stiffness of your lining? The usual answer is, actually I don't know. Because we never calculate it. It's just for continuity purposes. We never calculate it. The lining is supposed to stand up just like that, So I don't bother to calculate. But when you simulate a full 3D, you got to figure out what on earth to put in there. You know what I mean? And it's clearly not isotropic. There's some cross and isotropy there. So these are some of the consideration. Actually, structural elements are very hard to model. Okay? And of course, the question is, whether you should use 2D or 3D. To me, in all my consulting work, I usually don't use 2D because if they want a 2D, I won't do it because I say, look, if you want a 2D, my students all outside, they can run 2D perfectly well. I don't want to compete with them for their rice bowl, And honestly, it's fair. I think it's fair. Why should I don't need the money. You should go and find them. They are the one who need the money, But if you tell me that you want something special and you want a 3D and my students said they cannot do a 3D, fine, I'll help you to do. So this is usually what I do. And I over the years I've done quite a number of 3Ds, and basically I felt that the 3D in general, actually most problems are three-dimensional. To be honest with you, most problems are three-dimensional. Whatever our what do you call it, our idealization for 2D is really just an idealization. Okay, so actually, in fact, this is the wrong question to ask. Is 3D analysis useful? Because actually, ultimately, all real problems are three-dimensional. We live in a three-dimensional world. We don't live in a two-dimensional world. And so the question is whether a two-dimensional analysis is sufficient. If you think it's sufficient, by all means, go and use it. But now, actually, 3D analysis is becoming quite widely used in Singapore for construction work. And back in 1998, we wrote the first paper on 3D effects in ASCE. Okay, and that basically there are a lot of these effects, the corner effects, the three-dimensional circumferential effect. I will talk about it tomorrow in the Nickel Highway. Okay, the loading and construction sequence in the soil stratification, all kind of thing, all can lead to three-dimensional effects. So, yeah, I think that even if you're not running 3D, don't lose that 3D view, the 3D view in your mind, the three-dimensional view in your mind. You know what I mean? Don't lose that view. You can run a 2D, but don't lose the 3D view. I like to give you, and I think this is the last slide. I think this last slide, this particular friendly 3D, I don't think we need to bother about it. Okay, so we can, right. Okay, so maybe I just finish up with this last slide by just telling you something as simple as that. How many of you are familiar with deep excavation or have done some work on deep? You have done work on deep. Okay, you know in deep excavation, they always preload the strut. They always go in there and they preload. Now, I was talking to some engineers, and this happened on the Nickel Highway analysis. And I was talking to one of my colleagues, K.Y. Yong, who was advising LTA, the Land Transport Authority, on the Nickel Highway collapse. And he told me this, he said, I don't understand why we seem to be losing a lot of preload on the Nickel Highway. He said, we only getting 30% of our preloaded value remaining on the Nickel Highway. After a while, it was even in the early struts, in the upper level struts, they already saw it. They couldn't understand why this is the case. Now, there have been a lot of speculation as to why there is this preload keeps changing. You know. Now, there is also a guy in Singapore, one of my former students, New Jian Sin, wrote a paper about how between day and night you get changes in the strut load because of the expansion of the struts and all sorts of things. It can happen. But if you have a consistent loss over a period of few months, then it's harder to pin it down to day and night kind of fluctuation. So I decided, I said, okay, never mind. You just tell me what preload you put in at the start. That is the design preload. And I will just put it in first and see what happens. So we put in the preload. And we did a three-dimensional analysis. I will show you the analysis tomorrow. And the interesting thing that come out is what? We were getting 30%. And so I got me thinking straight away, you know, because I look at the result, I say, hey, I didn't do anything. Now, he might have hit something peculiar, but on my computer, I cannot possibly hit something that peculiar that I end up with about 30% of the preload. So I start looking at the thing. Now, it turned out, actually, the problem is very straightforward. A lot of people don't realize. In a preloading situation, you never preload the whole layer of strut at one go. You preload this strut. Then you preload that guy. When you preload that guy, the whaler moves back. Do you lose preload here? Right? Then you preload that guy. You lose a bit more preload. Then you preload that guy. You lose a bit more preload. So you find that all your struts are losing preload as they go along. Not in a uniform way, but in a substantial way they are losing preload. The problem with the two-dimensional analysis, I always tell people, even if you're running 2D, don't get into a 2D view. The problem with running a 2D analysis is this. A strut is just one line, one level of strut. You just go strut. And so when you put in a full preload, you just go straight in. It is as if you suddenly preload the whole layer of struts to that load. It never happened in practice. It never happened in practice. The contractor cannot have enough jacks to suddenly do preload few hundred struts at one go. It's just impossible. So he will go one by one, to the best of his ability. And to the best of his ability, when he do one like that, and then he do the next guy, this guy is going to lose preload. And so that's how we end up with 30% preload. It's a matter of construction sequence. And it's nothing, there's nothing devious about it. They just, human nature, just do one by one. And that was exactly what happened. And so I kind of told him, I said, look, this is a classic situation of unintended effect from the construction sequence. And as the guy has never done anything wrong, to me that construction sequence is perfectly normal. This is the kind of thing they would do. And yet it leads you to something like that. But you won't see it if you're doing 2D, because your 2D vision is, oh no, just whole layer, just going like that. Okay. Okay. I think I will leave it at that. Okay. Sorry, what is it? If the 2D analysis gives the same result as 3D analysis, then the 2D is more preferable. Yeah, but I can't understand the question, because in order to show that the 2D gives the 3D, you have to run both. Isn't it? But why would you want to run both? I mean, basically, you just run one. If you want to run a 2D and a 3D, you must well just do a 3D. Correct? You won't run a 2D and a 3D and then say, oh, the 2D and the 3D give exactly the same result. Therefore, the 2D is preferable. I don't see why you need to make that argument. That's my point. You know what I mean? Yeah. But in order to show your client, supposing I'm the client, how you going to prove to me that your 2D is as good as a 3D? So you have to run a 3D, right? You have to run a 2D, right? So basically, you are doing double work. But yeah. Oh yeah, of course. I do not disagree. I do not disagree. There are possibilities. I'm not saying that 2D should not be used. I'm not saying 2D should not be used. I'm just saying that even if you use 2D, do not use a 2D view to view the 2D analysis. Use a 3D view. That means your mind should be thinking 3D. Your run could be 2D, but your mind should be thinking 3D. You know what I mean? So then, at least even when you run 2D, you will know that you have made certain assumptions, but you think your assumptions should be okay. You know what I mean? The problem will come when people use 2D so often to the point that they think the system is actually 2D, when in fact it's not. You see? But actually some of the 3D effects are very, very, very subtle. I mean, the tunnel is a kind of situation that, for example, tunneling, okay, is a situation where you think it is going to be 2D, but in fact it's not. It's very, very 3D. Tomorrow I'll show you the Fort Canning tunnel where you can see it is very, very 3D. And there are some very surprising conclusions coming out of that analysis. And no, the reason why we ended up running that particular job was because the consultant had a big argument with the authority, the land transport people. And they could not convince the land transport of certain things. So one of the senior consultant says that we got to run a 3D. And that's why I ended up running it. I mean, I didn't volunteer for the job. I was asked to run 3D, so I said, okay, I'll try to do it for you. The same thing with the Nickel Highway collapse. The Nickel Highway collapse is a classic problem where it was designed on a 2D, but after the failure, we found a lot of 3D effects. So, I mean, to me, it is either the consultant has missed something, that somehow the 3D effects are not considered. But you see, to see 3D effects, sometimes you need to be very, very sharp mechanistically. I mean, the Nickel Highway is an example of a problem where you need to be really, it takes a good mechanician to be able to see that. You see, the reason is, I just give you a quick summary of what happened. The nickel highway is this nickel highway, right? I think you saw it. No issue. Now this is you can see that this is the portion that collapsed. And where this portion is coming in is on a curvilinear alignment. It's a curve alignment. Now, the consultant's idea is that because the radius of curvature is 300 meters, it's so big, I don't need to worry about 3D. It's going to be almost plane strain. Okay? The problem is this. When you have a curvilinear alignment, like this, you don't have that with a straight alignment. Okay? And the contractor did not use any veiler because he said, I go one-to-one, strut panel to panel, which is rubbish. When you look at it, that is a piece of rubbish. But in any case, the main thing is this. You have a curvilinear alignment. All right? And when you think about it, I'm just exaggerating it, but this is actually quite gentle. All right? This is plan view. The wall is looking down on the wall. All right? Now, supposing you have a wall on this side, the north side, coming in, then the wall line will be placed into compression because your radius is decreasing. So it's compression. On the other hand, if you have this guy going into the trench, then the wall line is expanding. The wall line is expanding because your radius is increasing. So you got tensile stress along the wall line like that. And when you look at the failure of the thing, do you notice something? This is the sound. Let me just stand back a bit. This is the southern alignment. This is the south wall. That's the north wall coming down. You can see the south wall, the panel breakup. It's almost panel by panel breaking up, and the breaking up is occurring right at the joint between panels. There's no steel. And the wall line just comes out, it just goes splitting up. So the wall is moving in, but something is pushing the wall in, but it's on a curve. So the guy has got to become longer. How does it become longer? The joints are cracked up. You see? You can see. Everyone. Like a tombstone, everyone. It's not just any old house, it's all cracked up like that. So I can always say it's easy to see so on hindsight it's easy to see. But actually if I'm an engineer designing the first time, I probably will be caught out. To be honest, don't you think so? I'll be caught up as well. So it's a very dangerous thing. As an engineer, you are responsible for a lot of these things, which you cannot. I mean, honestly, you say, if I'm an engineer, do I seriously expect every engineer to see this? I don't think so, honestly speaking. I would say 90% probably won't see it. Maybe more. Correct or not? More of them will not see it. But it's easy to see it when you have the computer study come out and you show the wall line breaking up. That is easy. That's hindsight. That is easy to see. So you can see how dangerous the engineering profession is. But when you think about it, when you go to court, the judge will say, but this is third year mechanics, right? You increase the radius, the radial strain is the change in radius divided by the original radius. There is also the circumferential strain. And you cannot say no. You can't tell him, look, I forgot all about all those. Correct or not? So it makes you shudder when you think about that. Actually, not so straightforward. Not so straightforward. Okay? But I mean, I'm not saying that nobody will see. I suspect that some. I mean, one of my very senior structural colleagues was the first one to see, Lee Seng Lip. The old man Lee. You remember the old man Lee? He's very sharp. He's the guy who told me, you look at those tombstones over there, they're cracking up because of tension. There has to be a clear line of weakness for them to crack up like that. Okay. So basically, is there any rule that I can teach you on this? There's hardly any. But really, do I expect everybody to be able to see it without hitting it first? I don't think everybody would be able to see. I would say majority would not see it. You know, I probably will miss it actually, honestly speaking. But of course, I did the analysis, and the analysis taught me that it exists. And I can show you the analysis tomorrow, the animations tomorrow. I'm trying to dig up the animation tonight so that I can show that. It's not in your notes because I thought that there won't be time. But if you're interested, I can show you the animation tomorrow, and you can take a look at it and see what, whether it, what it looks like. So you can see, you can even see the strut buckling, section by section struts buckling. I mean, it's jumping from strut. The load is jumping from one strut to another because the moment this strut buckle, it goes, the load shoot over to the next guy, and then the next guy go, it shoot over to the next guy. You can just progressive collapse. Very interesting. Okay. Which one? Oh, the big thing there. It's just a shaft. It's just a launch shaft. The reason why, actually, this is another stupid thing they do. This part here, the whole thing is tunnel. It's tunnel. But because this is the place where 4 tunnels intersect each other, it's called an interchange box. The interchange box, they have to cut down, they have to dig down this particular section only, dig down to cast the interchange box. Then they fill it back up. On all other sections, is all bored tunneling. All bored tunneling. So the launch shaft, on the other side of the launch shaft there, going that way, is all bored tunneling. All bored tunneling. So basically, there is no excavation on the other side. The excavation stops at the shaft. Yeah, it bends to what? Yeah. You can see. In fact, I can show you this one. See, this is the shaft. You can see the shaft there at the end. You can see the shaft is bending towards the shaft. It's bending towards the shaft. But it's a very poorly designed. It's one of those things that I think that there are a lot of legal lessons that we can learn as engineers. If you're going outside, I don't know how many of you are intending to be professor, how many intending to be practicing engineer, but there's a lot of legal lessons to be learned. The first lesson is, don't anyhow give your Plexis file to third party. Serious, I'm serious. I mean, triaxial is okay. I give you triaxial, no problem. Verification problem, there's no problem. But I tell you how it landed AECOM, AECOM, Monza, how it landed them in problem. They never were involved in this temporary work design. Okay, AECOM was the design of the permanent structure. The permanent structure. Alright? So they designed the permanent structure. Then the contractor, which is a Japanese contractor, and so you see, this is partly the problem with the government as well. If you are a government engineer, and you look at the list of tender prices, and there's this guy that's 70% lower than the next guy, what is the thing that must go through your mind? Some alarm bell, right? Why is this guy so much lower than the next guy? There has got to be some questions being asked, but no question was asked. Design and build, no question was asked. Alright? So the contractor got a job. He's a Japanese contractor, Nishimatsu Namchang, with a local joint venture. Got a job. And then, when it comes to the temporary work design, they got AECOM to do a design for them. And AECOM gave them a design. And they decided that design was far too expensive. So they said, no, I don't want your design. I'm going to do my own design. And in those days, they are allowed to do it. So they got a few engineers, they bought a copy of Plexis. Okay? And the silly thing was what? They don't even know how to use Plexis. So they got my friend, who is the CEO of AECOM, Monsos, in those days, and said, look, can you just give me an example file? An example file of... So AECOM, very simple. Since I did a first cut design for you, and you say it's too expensive, I give you that file. I give you that file. That was a base file that they used. And that file uses method A. And that got AECOM into deep trouble. So the lesson of the story, don't anyhow, even your best friend, don't give him any file. Because anything happen, you can be in court. Because you know why? You don't need to have to sign on a drawing. The judge says, any kind of engineering output from you is liable. Any kind of engineering output, not just something with a signature, but any kind of engineering output. It sets a terrible precedent, right? I mean, anything. I give you something and then next moment, hey, I'm in court, I don't have to sign on it. Okay? So these days when people ask me for things, I say, my point is very clear to all my friends in Singapore. You don't engage me, I talk to you over the phone. Anybody asks, I disclaim any such phone call. As far as I'm concerned, this conversation never took place. Alright? If you pay me, I have to charge you for professional liability. I have to. That's what I have to do. And that is the result of the nickel highway, because everybody realized that whatever you produce, you are liable. If it can be traced back to you, even an email, even anything, you are liable. So that project file was traced back to AECOM, and AECOM was liable. Why you teach? You see, AECOM cannot say, this is just an example file. Then the judge will say, yeah, you are showing them the wrong example. Right? You are showing them, how can you be showing people negative example? You see? So engineering is very dangerous business. It can get you in a lot of trouble. But it's also good. It's a good money business because because people realize the risk, they will charge a lot more. Geotechnical engineering charge a lot more. Then structural engineering in Singapore is not worth the money. Geotechnical engineering is worth the money. So a fully qualified geotechnical specialist professional engineer is typically worth at least $15,000 a month. That's the kind of money. Of course, it's risk money, If you don't pay the kind of money, nobody can do the job. And even then, there are only about 50 persons signing things off in Singapore. You see, I'm a specialist PE, but I never sign. You see, I pay for the license every year, but I never sign. Because the university doesn't allow me to sign. The university says that this is all too dangerous. You shouldn't be signing. You can be giving a second opinion, but you should not sign off a calculation. But even now, giving a second opinion is going to land you in trouble. Because if I give you a GeoFEA project file, I can land myself in trouble. That's the kind of thing. Yeah, it's true. Life is tricky. Yeah. Anchor will be less likely. I tell you why. Because anchor has a lower stiffness. So if the wall, anchor, you're talking about ground anchors, right? Okay, anchors are less stiff. Struts are more stiff because they're bigger section, shorter. So all in all, it makes their stiffness higher. Now, a system with a high stiffness, when you subject it to movement, the load will release faster. The load will release faster. Very simple. If you have a system that has a very low stiffness, all right, then it will not release the load so readily because, let me just try to. Let's say you got two systems. This is the force deflection curve. One system is like that. The other system is like that. All right? For the same amount of movement back from here, say, if I move back from here to here, this one only reduced the force by so much. That's the anchor situation. This guy reduced the force by that much. That looks more like a strut situation. So basically, the anchor is more flexible, and so it has a tendency to hold the load better. But people like the strut because in Singapore it's very hard to use anchor. The reason is very simple. You're going into someone's property, and I will never let you come into my property. Even if there's nothing, even if I think there's nothing wrong with my pile, I won't let you come in. You see that because you know why? It's my property. Why should I let you come do work in my property? If I agree to let you do work in my property and your anchor come in and something go wrong with my pile, then who is going to be responsible? I may have to tear down the whole building. I cannot afford to do that. So in fact, it is almost a foregone conclusion. If you use anchor and you have to go into someone else's property, no go. It's no go straight away. No go. All right. That's the first reason. The second reason is that because the strut is stiffer, by by analogy, you can say that if you have a movement forward in this direction, some compression effect, the strut will pick up load faster. It's more positive. It's much more positive. So the strut is more positive. It's almost exclusively strut. Now, in anchors, I have seen people use anchors, but only by hillsides, not in the city area, way out in the countryside kind of thing. I've seen people use anchors, but it's a very, that's another issue, going into other people's property. Recently, one of my friends asked me, it's also a very tricky issue. Even if there's nothing wrong, I say nothing wrong, I will make it look as if there's a lot of things wrong. So you cannot come into my property. If you want to do some ground improvement work in my property over my dead body, you want to do, you do it on your side, don't do it on my side. I mean, correct or not? This is the way it works now, because there's no sentimentality, you know. Because you know why? If I let you create a cement block in my property, within my boundary line, that cement block is yours or mine. If it belongs to me, okay, if anything happens, that cement block is causing any problem, I have to fix it up. So firstly, it doesn't help me, it helps you, but I have to fix it up. If you say it is your property and it's not mine, then I lose property. Because my property just gotten smaller. Or why should I reduce my property? You know what I mean? So there's no such thing as friendship. When it comes down to that, it's simple as that, business. Okay? So usually we don't like to use anchors. Anchors is not a major thing in Singapore. Not a major. Strut is a much more common thing. But I think that with time to come, if you're doing it in India, for example in Mumbai, old Mumbai, I am sure nobody will let you put an anchor underneath those old buildings. Why? Huh? You use ground anchors. You go underneath their building. You don't care. Did you ask them? No. In Singapore, you have to ask because that is their property. So the lawyer has a right to stop work. The lawyer has the right to stop work. So in Singapore, we have to ask. Okay. Now they change the law. Anything below 30 meters, you don't have to ask. But the top 30 meters is their property. You have to ask. You know. So that's why in Singapore, nobody wants to use anchor. Okay. Any other thing? Basically, if you ask me, if you have done your ground investigation properly and you know for sure where the other guy's piles are, you shouldn't cause a problem if you anchor into rock. Because really your anchor, there's a free length. And a free length is not going to do anything. But hopefully the rock is strong enough. But if I'm the owner of the property, I won't let you come in. The reason is very simple. If you make a miscalculation, I have to pay for it. Why should I take the risk? My point, why should I take the risk? You know what I mean? I got nothing out of it. Because I'll ask you, what do I get out of it? If you can give me some goodies, maybe I can think about it. But if you give me zero goodies, there's nothing to think about it. You know what I mean? It's strictly a business deal. It's a strictly business deal, this kind of thing. There's no sentimentality. So basically, if you say it's just to help your client, sorry, kind of, you know. That's the way it works. So basically, and also the thing is, a lot of the older buildings in Singapore, because Singapore is also a changing society. You can say that for buildings that were built in the last maybe 10 years, you might have very good as-built drawings, what we call as-built drawings. But buildings built in the 1960s, 1970s, don't count on it. You don't even know whether the piles position are correct. That's the thing. So basically, nobody knows for sure where some of the piles are. And some of the pre-war buildings are even worse. They use wooden piles. We call them bakau piles. It's a kind of timber that you just drive in, you know. And there's no as-built drawing, no engineering drawing, none whatsoever. So the question is, what is the chances of you hitting something? Well, possibly quite reasonably high, you know. So that is the only thing is that I think if you are, my sense is that if you are driving below low-rise building and on good ground, you probably have you're probably below the footings anyway. Is the building on foot? Are the buildings on footing down here mainly? Sorry? Oh, open footing is less of a problem. But in Singapore, usually a lot of buildings have piles. These days, I would say that even 2-story houses are on piles. If it is on soft clay, they would want them on piles. Okay? The reason is because they are concrete building and they cannot take the movement, the kind of differential movement very well. So they will be on piles. And almost every public building will be on piles. It's very heavily piled. Singapore is a very heavily piled country. Everything is piled. You know? So basically all the tall buildings are piled. If you go down to the town and you want to dig a big hole next to a tall building, you can be absolutely certain that building is on pile. And all around you, those buildings will be on pile. You see, footing may be less of a problem because footing don't go very deep. Footing don't go that deep. They're only a few meters deep. But piles can go 30, 40 meters deep. You know. So basically, that's one of the reasons why in Singapore, nobody wants to allow that. I mean, there are some situations where you anchor into the hillside. That's fine. There's no one there anyway. You know. So basically, there's a lot of this thing going on in Singapore. So that's why strutting is more preferred, more preferable than anchors. You know, I have used anchor very, very rarely in Singapore. Very rarely. There's one when there's a hill collapse and we did a remedial job and it was anchor. But because it's a hillside, it's a forest anyway, no one's there. So we just do anchorage. So it's easy. You know. All right. All right. Okay. Any other question? I think, my goodness, 3:30. You need time to practice, right? Okay. Maybe we better split up and then you go for your ground floor practice. We meet again tomorrow morning. I finish the whole thing off. I'll try to get some animation to spice up the session a bit. Is that okay? All right. Ken?
It's 3:30.